All right, so we're going to talk, we're basically done with the molecular shape stuff, okay? And so we're going to talk now about polarity. Now on your notes, I don't think we filled out these examples, did we? Okay, so what you can do on that, because I'm pretty sure both of these were on the other sheet that we did. So just make yourself a note here, examples on other set of notes, okay, or something like that, just to remind you that you can look at that big chart we filled out with the gumdrops and the marshmallows, and that gives you way more examples than we actually had on the notes here, okay, so we're not going to worry about that. So we're going to start right here on Roman numeral 5 where it says bond polarity, okay, so that's where you are in the notes. Okay, so when we talk about polarity, we've already kind of talked about this a little bit, haven't we? A polar bond, like polar versus non-polar, right? And the idea here is, does the overall molecule have a charge? Okay? So the way that we determine that is based on electronegativity differences when there's only two things. Okay? Excuse me. And that we've already done, right? You can look at your electronegativity chart. You can see chlorine is a lot more electronegative than hydrogen. So you remember the little soup ladle thing that I drew? Partial negative charge, partial positive charge over here. Okay, it's not like this chlorine is completely pulling the electron off of the hydrogen. So it's not like it's a 1 plus and a 1 minus, but it's kind of more minus over here and kind of more plus over here. Okay, does that make sense? So it's like the poles of a magnet. You've got the positive end and the negative end. Okay? All right. Are you finished? Then how come you're not? Okay, so on bond polarity, first thing that you would do on any of these to figure out the polarity is you draw the Lewis structure, okay? And the Lewis structure for HCl basically just looks like this, okay? So the HCl is polar because it has a positive end and a negative end because there's a difference in electronegativity. All right, so if you have just two atoms, it's really easy to figure out whether it's polar or not, right? You just look at that difference in electronegativity and that will tell you. Where it gets difficult is when we start talking about molecules that we've been dealing with when we've been talking about the molecular shapes, okay? How do we know if those are polar or not? Okay, and this is just elaborating on that. Do you have to fill this in your notes, or is it already filled in for you? Cl has a greater share in bonding electrons than the H does. Okay, you don't have to fill that out. Okay. All right, so that means the Cl has a slight negative charge, which again is kind of this. It's really a Greek lowercase delta. Okay, but I think it looks like a soup ladle. So I'm going to call it a soup ladle negative, soup ladle positive. Okay. Oh, and there it is. Now another way to represent it, if you like this method better, you can actually point an arrow towards the more electronegative atom, okay? And so this arrow down here basically just shows, and I think I did show this to you also, but this arrow basically shows you, okay, the electrons are moving more in this direction, okay? All right, so polarity is why oil and water won't mix with one another, okay? Oil is nonpolar, water is polar. So polar things don't mix very well with nonpolar things, and nonpolar things don't mix very well with polar things. Okay? There's a little expression we have in chemistry, and I don't think this is on your notes, but it's likes dissolve likes. You might write that down. Okay? And it basically means that things that have a charge tend to dissolve, other things that have a charge, okay? So you think about water and sodium chloride. Sodium chloride is what kind of compound? Ionic, covalent, polar, nonpolar, what is it? Thank you. Sodium chloride. Sodium's a metal, right? It's on the left side of the periodic table. Chlorine's a nonmetal. So you put a metal and a nonmetal together, what's that going to be? That's ionic, right? It's an ionic compound, okay? So there's a charge there, right? And in the ionic compound, you have charged atoms. So you put that into water, which also has a charge to it. Water is polar. Then what do you think is going to happen? Well, you know what happens. When you put salt in water, what does it do? It dissolves, right? And the reason it dissolves is because they both have a charge, okay? And so they're attracted to one another, so the salt dissolves. Oil doesn't really have a charge. The molecules that make up oil are fairly non-charged, okay? So you put it into water, it's not all that attracted to water, and the water is really more attracted to itself than it is to the oil, so the oil doesn't mix with the water, okay? Oops, I'm going to keep doing this. It says the two will repel each other. I'm not sure if I like that. Thank you. It's not really a repulsion, it's just a lack of attraction. The water is more, like I said, the water is more attracted to itself than it is to the oil, so it's, you know, it's just going to stay by itself. It doesn't really want anything to do with the oil, and the oil is not all that attracted to the water, okay? So it's not that they repel one another, it's just that they don't mix because they're not attracted to each other. Water molecules in cage around the hydrocarbon chain. Okay, so what will happen sometimes is these things, it will seem like they're trying to get away from the water when they're in the water. So if you, let's see, I'm looking at my only PBS student is not in here at the moment, I think. Oh, wait, but you're taking it now, so I'm thinking about ones who have taken it in the past. But you know how we talked about hydrophilic, hydrophobic? That's kind of what this is, okay? It has to do with polar and nonpolar. So the oil is hydrophobic, and it doesn't really mean that it hates the water, it's trying to get away from it, really. It just means that it's, you know, more attracted to itself, and so it kind of clumps together here in the middle of all this water, so you end up with these globs of oil inside the water, okay? And the same thing happens with, you know, with amino acids and the way they interact in water. Okay, so that's all the notes have on polarity, and I'm not sure that that's enough. So what I want you guys to do is pull out that worksheet from yesterday. And remember how I said not to fill out the last two columns on that worksheet? One of those columns we're not going to fill out, period, but one of the columns we will. The one that says hybridization on it, well, here, let me just open up the worksheet again here. The one that says hybridization, you can just cross that column completely off. Okay, we are not going to do that column at all. But the polar and nonpolar thing, I'm going to teach you a little bit more about how to tell whether something is polar or nonpolar. And it all, again, it comes back to the Lewis structure, okay? So let me just kind of run through several of these with you, okay? So with BCl3, again, the Lewis structure is going to look like this. Okay, and something you probably do want to write down on your notes. Sorry, I should have had you do this while we were just talking about the notes. This is important, and I'm going to erase this on here in a second, but symmetrical, you do need to write this down, okay? This will help you. Symmetrical equals non-polar. Asymmetrical, no, that's not right. I stopped in an unfortunate spot there. Asymmetrical, there we go, equals polar. Okay? What I mean is, if the molecule in general is symmetrical, and it needs to be symmetrical in 3 dimensions, and that's a little bit tricky sometimes, okay? But if it's symmetrical, then it's nonpolar. If it's asymmetrical, that means if it's off balance, it's not exactly the same on every side, then it's going to be polar, okay? If it's off balance, that means you probably have a charge on one side or the other. That makes it polar. If it's completely balanced, then there is no charge in the molecule, and it's completely nonpolar, all right? Does that kind of make sense? And I'll show you as we go through how to tell what's symmetrical and what's not symmetrical. Okay? Okay. So BCl3. BCl3 is trigonal planar, right? For its shape. So really probably a better way for me to draw this would be like this. Put a Cl here, put a Cl here, put a Cl here. So we've got 120 degree angles between each of these. Okay? So what do you think? Symmetrical or not symmetrical? Well, these are all 120 degree angles, right? That looks pretty symmetrical to me. These are all chlorines, right? That's a boron in the middle. So that's symmetrical, okay? Because these angles are all the same. The atoms around the central atom are all the same. So if it's symmetrical, that means that it is non-polar. And you're right, equilateral triangles do have... no, equilateral triangles have 60 degree angles, don't they? Because they have to add up to 180. Yeah. Okay, so that's going to be non-polar because it's symmetrical. All right? Next one, CH4. Now, you have to be a little careful with this one. When we draw the Lewis structure for this, normally we're going to draw it like this, okay? Is that really what that molecule looks like as far as its shape? What does it really look like? Right. It's a pyramid base. You remember when we built the tetrahedral? Okay? So it's got a pyramid base and then one on top, okay? But every single angle is 109.5, right? So in 3 dimensions, is that symmetrical? It's a little tricky. But if they're all 109.5 degree angles, they're all the same, would that be symmetry? I would say yes, okay? And symmetry in chemistry is not always exactly what it is in math. Because in math, you think about, can you divide it in half and do you have the exact same thing on one side or the other, right? But here, if all the angles are the same, you got the same number of atoms around, or the same type of atom around the central atom, then that's probably symmetrical, okay? So again, if it's symmetrical, we're going to call it non-polar. Okay, how about NH3? NH3 looks like this. Does that look symmetrical? Well, kind of on 3 sides I have hydrogens. And on the other side, instead of a hydrogen, I've got a lone pair of electrons, right? That's probably not symmetrical. Does that make sense? Okay, so there's probably a charge on one side of that molecule, a positive charge on one side, a negative charge on the other side. So we're going to call that polar. All right? Now, I gave you the symmetry rule. That was important. Another thing that I want you to write on your notes in the polarity section. This is also really important. Almost always, there are a few exceptions to this, but almost always, lone pairs on the central atom equals asymmetrical, which also equals polar. Okay? If you have lone pairs around the central atom, almost always, that's going to be asymmetrical, which means it's a polar molecule. So if you see lone pairs on the central atom, you should be thinking polar. Does that make sense? All right, let's look at the next one and decide if that's polar or non-polar. Whoops. Probably should have left those. Well, I've got to scroll down, I guess. You know what? I'm going to take a pass on NH4. That's a polyatomic ion. Kind of weird. So I don't want to deal with that one right now. I'm not going to give you any polyatomic ions for these, okay? H2S, though. Let's look at H2S. So H2S, we've got sulfur connected to hydrogen, 2 lone pairs. Well, that looks pretty symmetrical, doesn't it? Well, here's the thing. In 2 dimensions, that looks symmetrical, right? But do you remember what happened when we pulled 2 of the marshmallows off of the tetrahedral? What did it look like? Do you remember? No, that wasn't seesaw. When we pulled 2 of the marshmallows off, it looked bent, right? You remember that? Okay, so if I was really drawing this the way that the shape actually is, it's going to be more like this. Does that look symmetrical to you? No, it shouldn't, okay? Because this sulfur, this is the negative one, right? So this is going to be the negative end of this molecule. This is going to be the positive end down here, okay? It's not balanced, okay? Because you've got electrons up here, you've got hydrogens down here. So it's a lot more negative on this side of the molecule, okay? Again, if you remembered the rule that I just told you, what was the rule? Lone pairs almost always equals polar, right? So there are lone pairs on the central atom, that's going to be polar, okay? Still got a little bit of time. Guess how you can tell without even redrawing these? How can you tell if something has a lone pair on it? Well, sort of. Okay, yeah, I don't know if you can always say that rule specifically, okay? Okay, and I heard a couple of you say it. If they have non-bonding domains. What is a non-bonding domain? It's a lone pair on the central atom, right? Okay? So if you look at this, SO3 right here, number of non-bonding domains is 0, right? So we could probably say that's going to be non-polar. See how that works? TCl3, it has a non-bonding domain. In other words, it has a lone pair around the central atom. So we can probably say that one's going to be polar. Okay? Now, there's another situation that I don't think is on this worksheet. Oh, no, here. This one. Well, but that's the polyatomic ion. Here we go. This right here, H2CO. Okay? H2CO has no lone pairs, right? If I draw the Lewis structure for H2CO, it's going to look like this. Does that look symmetrical to you? Now, I've got an oxygen on the top, and, you know, then I've got hydrogens down here. So if you have different atoms, that's another thing you should write down. Different elements around the central atom, that equals polar, okay? Because it's going to be asymmetrical. Does that make sense? So we've got hydrogens and an oxygen on that central atom. So because there are different atoms, different elements around it, that's going to be asymmetrical. So that makes it polar. Okay? The polar-nonpolar thing is a little bit tricky. If you just remember the lone pair rule and you remember the fact that if you have different atoms around the central atom, then it's probably going to be polar. Then you're okay. All right? Those are the main things that you really need to remember here. Now, there's more to it than that, but that's about as much as we're going to cover in here. Okay? So if you want some extra practice, there are a lot of these that we didn't go through. You could practice writing the Lewis structures for those and making sure you understand whether they're polar or not. And we will have a quiz on this on Monday. We'll probably review it a little bit first, just because it's a Monday. Okay? But we will have a quiz on Monday.